All right, today we are pulling back the curtain on the world you see every single day. We're going to explore the hidden genius of civil engineering, the science that designs and builds the very world we live in. We're going to use the Civil Engineering Guide as our source material to see the invisible blueprint that shapes everything around us. Okay, let's jump right in. No, really think about it for a second. That bridge you drive over, the office or house you're in right now, the clean water that comes out of your tap, none of this happens by magic. It's all the result of some seriously careful planning, endless calculations, and a ton of hard work. It's all part of this invisible system, this master plan that makes sure our world, works. So here's what we're going to cover. We'll start by peeking inside the engineer's playbook. Then we'll get into the real secrets of what makes structures so strong. After that, we'll follow society's lifelines, things like water and transportation. And finally, we'll look at how all this engineering is actually building our future. So what does this master plan actually look like? Well, it's not really a single document. It's more like a massive library of knowledge, a whole collection of different fields that all have to work together perfectly. You can think of civil engineering as this huge collection of different rule books. You've got structural engineering, which is all about bridges and buildings. Then there's environmental engineering, which handles our water. You've got highway engineering for our roads and surveying to map out the land itself. All of these together form that invisible blueprint, this whole network of rules and formulas that builds our world. Let's start with maybe the biggest question of all. How do we build things that don't fall down? It all comes down to understanding forces and materials on a really, really deep mathematical level. A huge concept here is something called resilience. Just think about a rubber band. You can stretch it, right? It absorbs all that energy. But when you let go, it snaps right back. It recovers that energy. Structures have to do the same thing. It's why a skyscraper can actually sway a few feet in the wind without breaking. It's designed to bend a little under pressure and then just return to its original shape, totally fine. That's resilience. So how do engineers actually calculate all these forces? Well, they use principles that look deceptively simple, like this one. A moment is really just a turning force. Imagine you're using a wrench to tighten a bolt. The force you put on the handle creates this powerful twisting force on the bolt itself. Engineers use this exact same idea to figure out the turning forces on every single part of a building, making sure nothing gets twisted beyond its breaking point. Okay, I know this sounds super technical, but just think of it like an unbreakable law of physics for builders. Shear stress is that sideways cutting force, kind of like scissors. And this rule tells engineers that in any material, there's always a sweet spot, an angle where there are only pushing or pulling forces, and absolutely no cutting force. Finding that sweet spot is everything, because that's the point of maximum stability. It lets engineers know exactly how something will behave under pressure and keeps it from failing. And this is so crucial. Engineers don't just use one material for everything. No way. They put together a whole team of materials. Steel, it's fantastic at handling tension, being pulled apart. Concrete, on the other hand, is an absolute rock star at handling compression, being squeezed. So when you combine them, like in reinforced concrete, you get the best of both worlds. And then you have specialized parts like these gantry girders, which are designed to handle all sorts of crazy forces coming from different directions, like in a factory.
Okay, so we've talked about things that stand still. Let's move on to the dynamic systems that keep our cities alive. The lifelines that bring us the good stuff and take away the bad.
It seriously feels like magic, doesn't it? You turn a handle and bam, clean, safe water just appears. But behind that one simple action is this massive, incredibly complex network, all designed and maintained by engineers. This here lays out the pretty incredible journey your water takes before it gets to you. It's not just a pipe from a lake. From its source, it goes through this whole multi-stage cleaning process. First, they screen out the big stuff, like leaves and branches. Then, they let smaller dirt particles settle to the bottom. And finally, they disinfect it to kill off any nasty bacteria. Every single step is a precise engineering puzzle, all to make sure the water in your glass is perfectly safe. But here's the thing. Engineers can't just build for today. They have to build for tomorrow. How do they do that? By predicting how many people will be living in a city. And as you can see, they use different models. For an old, stable city, they might assume the population grows by a steady number each year. But for a young, booming city, they'll assume it grows by a certain percentage, which means it grows way, way faster. Picking the right model is the key to making sure our infrastructure doesn't get overwhelmed down the road. Next up, let's talk about the science of getting from point A to point B. The roads and railways we use every day are just amazing feats of engineering, all designed for safety and efficiency. You've definitely driven on both of these, even if you didn't realize it. You've got your flexible pavement, like asphalt, which is built in layers that push the weight of a car down into the soil. And then you have rigid pavement, like concrete, which acts more like one solid slab that spreads that weight over a much bigger area. One isn't necessarily better than the other, they're just different tools for different jobs, depending on traffic, weather, and what the ground is like.
And this just shows you how incredibly precise this all is. A gradient is just how steep a hill is. The guide tells us that if a road slope is less than 4%, it's gentle enough that engineers don't need to make any special tweaks for curves. But any steeper than that, they actually have to adjust the road to fight the forces that are trying to pull your car sideways when you turn. It's such a tiny rule, but it's one of literally thousands that keep you safe without you ever even thinking about it.
And it's not just roads. Have you ever been on a train and felt it kind of lean into a curve? That's totally on purpose. It's called superelevation. By raising the outer rail just a little bit, engineers use gravity to pull the train inward, which perfectly cancels out the force that's trying to fling it outward. It's this brilliant little trick that lets trains take corners at high speeds safely and smoothly.
Okay, so we've seen how things stand up and how we all get around. To finish up, let's take a quick look at how civil engineers are using all these principles to design the world of the future.
Today's engineering is all about data. A GIS isn't just a map. It's more like a living, breathing model of the world. Engineers can layer all sorts of information on it. Things like population density, flood zones, soil quality, you name it. This lets them see complex problems in a whole new way, run simulations, and plan huge projects with a level of insight that would have been science fiction just a few decades ago. And really, this brings it all home. When you boil it all down, this is what civil engineering is all about. It's about ensuring public safety by calculating the exact force on a bridge. It's designing for sustainability and efficiency, like that incredible journey your water takes. It's creating human connection through roads and railways designed with pure math. And it is always, always about planning for the future. So the next time you drive across a bridge or turn on the faucet, just take a second to think about the invisible blueprint that's holding it all together. After getting this peek inside the playbook, what part of your world are you going to see with an engineer's eyes now? Thanks for joining me.